Hello, welcome to a series of videos describing the operation of the converging and diverging nozzle. I will first make an outline of 8 characteristic regimes that the nozzle flow can assume, and then I'll go separate pages with the same template going one by one. This nozzle, particular nozzle geometry, is given in example 11.8 in monsoon, and its area is being defined as 0.1 plus x squared, basically x going from minus 0.5 to plus 0.5. And given that radius is square root of area over pi, because area is pi r squared, then we can solve for radius, which is square root of 0.1 plus x squared divided by pi. And this is the contour of the radius shown in the picture. We have the flow going from left to right, and we'll just label some characteristic positions. This is upstream position in some kind of reservoir we can think of where velocity is 0, so we'll denote that as 0 position. Then we have the throat position T here, and we have the exit position E, and some point farther downstream which we'll call B, standing for like back pressure, back conditions. And these would be mainly, we'll introduce some other later as we go through details. So let me briefly just mention each of the cases, and then I'll go to each of them separately. So first, case one is the most trivial one: no flow. You have that nozzle sitting on your desk, watch it. Nothing is going to happen in it. There's going to be no flow because there's no pressure difference between inlet and outlet. It is the pressure difference that drives everything else, and it is the geometry of the nozzle that determines what happens for a given pressure difference. So in that case we have K0, basically constant pressure all along. This is the pressure ratio diagram with pressure divided by upstream pressure. If you imagine that this nozzle is drawing air at 1 bar at its inlet and has different back pressure here below 1 bar, then you would have basically this equals to pressure in bars itself, because P naught is equal to 1 numerically. And of course for no flow we have Mach number equal to 0 everywhere, so that would be the case 1. Then we have case 2. Now we just reduce the back pressure for a tad, so that there is some flow going in, but that's definitely subsonic. Flow. And so as we reduce pressure here very little, then we'll have some symmetric condition with a minimum at the throat, and it's all subsonic, and it's similar very much to incompressible flow. Similarly, Mach number is now at the inlet here a little above 0, and as the fluid accelerated goes up to some value and then symmetrically goes down to the same value. So this was case 2. Let's write them. Okay, so now we have case 3, which will be subsonic choked. In this case, we've reduced the pressure PB to such extent that the pressure at the throat goes all the way down to its critical value of choking pressure. This example here is for air. Basically, we'll say here air kappa is 1.4, and for air that critical ratio is 0.528. And now when that happens, the pressure is going down along this particular path, reaching the critical pressure and going back up again in a symmetric fashion, again reaching subsonic, so that's the case 3. And Mach number correspondingly goes up, reaches the value of 1, which is the critical Mach number by definition, because we call this critical condition where Mach is equal 1, but because of relatively high back pressure, it decelerates back to subsonic regime. Then we can have cases, I'll just write here case 4, case 5, case 6, case 7, and case 8. Lots of cases. So let me just go over them, not in this particular order, but let's start with case 7. So case 7 will be supersonic isentropic matched exit. Sorry. So this case is such that exit pressure is well matched by back pressure, and essentially the pressure drops as the fluid accelerates further, reaching its design value. We'll talk about that later. And similarly, Mach number goes up and reaches its design value at the end. Now that we have that limited case, let's go back to case 4. If we have reduced back pressure below case 3, the fluid will have to flow subsonically, and in subsonic regime it will basically decelerate, pressure will go up here, but at the same time pressure after the throat, because this is below the case 3, will go down. So in terms of Mach number, it will follow this route to some extent, and then at some point the only way these two curves can match is through a shock wave somewhere. So there's going to be exit pressure, exit Mach number in the subsonic region below 1, and a jump in Mach number, which is the shock wave. So this is case 4. As we move down further, the shock moves closer to the exit until we reach the regime for case 5, in which Mach number is subsonic right at the exit after the shock, but so we had case 4, which was subsonic exit, shock inside. And then case 5 is again subsonic, shock at the exit. So what about cases 6 and 8? Well, they are kind of similar to, they're between case 5. You guessed by now that these cases are arranged by decreasing back pressure, not necessarily by exit pressure, because we don't control pressure at the exit. What we do control is pressure, back pressure. So if we have some back pressure here that's higher than case 6, so this was case 7, sorry, and I'll write here case 6, 7, 8. So in case 6, okay, this was case 7. In case 6, we call this nozzle overexpanded. Basically, the pressure at the end is below the back pressure, and so it's supersonic, over expanded. Then similarly, case 8 is with the back pressure a little bit below the design pressure. So this was case 6, this is case 8, which is supersonic underexpanded. Okay, so this is a summary of all cases together, and in the next video we'll start with the first 3 cases.